Hi everyone, second video on vectors. Hopefully watch the basics, and that we got up to a point where we were describing vector line equations and how that worked, and we're going to go back over that in a second just to recap and see how that works in autograph. Here are the skills that was mentioned to you at the start. In this video, we're going to cover this intersecting line equations. In the next one, the dot product, that will help us find angles between lines. And we're going to talk a lot about that in class, really, about why and how it works. But really, the video is just going to help. Well, you can see the dot product written here, actually. The video is just going to help you use it, but in class, we'll really understand it. But for now, we're going to focus more on forming straight line vector equations and intersecting line equations. So let's get going with that. So find the vector line equation between the points A 5, 6, 3 and B 9, minus 4, minus 5. Now, hopefully we roughly know what's going on here. We need to let's do this through autograph. So I've got 5, 6, 3. Oops. Okay, so this is the origin here. I know, look at that, 3D autograph going up in the world. So we've got 5, 6, 3, 5, 6, 3. That's the point A, sorry, that cube that just turned up in space. And also we've got 9, minus 4, minus 5. So there we go, there's our second cube in space. So this is our A, and this is our B. Now, how do we find a line equation that goes all the way through them? So a line which goes through here, you can see that we can twist this about. Oops. We can twist this about, the axis about, so maybe it looks a bit nicer there. So therefore we have this line going through this point and this point here. But how does that work? Because we know that this is a vector A, which was 5, 6, 3, and that's that A relative to the origin, remember? Alright? So to make it even more pronounced, let's put that in autograph as well. So can you see, there's the origin to the point A. So let's get rid of that line. Origin, so origin, point A, line segment between them, and then origin and point B, line segment between them. These are the vectors describing A and B, aren't they? Right, the red and the purple. But like we talked about, we need a line going through A and B that continues all the way for infinity. How does that work if I'm starting at the origin here? This is the origin. This is my vector A, and this is my vector B. Well, as you know, first off, we need to get onto the line, and this is the line here, isn't it? Right? To get onto the line, R equals, to get onto the line from the origin, I first need to go up A. So equals A plus, now, as we've said, what does this R represent? R represents any point on the line, doesn't it? Any point on the line. So this point here could be R, couldn't it? Right? So there's our vector R. That's what I'm talking about. I've gone from the origin to A, so I'm here, and now I need to move up to R. But all I don't know the direction of this line yet, do I? All I know is this point in space where A is here, and this point in space B where that is here. And from A to B, or from B to A, from what it looks like on what I've drawn, it really doesn't matter. From B to A, I can see that that direction is the same. So if that's the vector B to A, And this will be the vector b to a as well, won't it? Right? But clearly that's too long because r is over here. So can you see I'm going a plus, we've talked about this before, b to a, but some amount of b to a. It looks like a quarter of it or maybe a half of it, but I don't, r could be anywhere. So that's why I put a lambda on there as well, okay? We have talked about this before, and I'm just really reiterating it. So this is called the direction vector, okay? Because that dictates the direction of the line, doesn't it? So A to B, or sorry, B to A here is now your direction vector D1. That's what's happening in space. But if we were, that's through 3D autograph. We don't need to use 3D autograph. All we need is a 2D picture, and you can clearly see what's going on now. Yeah, here's the line, here's a point R. In order to get to R, I'm going 0 to A first, that's that bit. That gets me, so gets me on the line, and then I need to apply this direction vector A to B however many times to get to any point on that line. Okay, that's line equations. Example 2. So this is the proper question now, and you'll see how practically things work. So first it says find the vector line equation between the points A with position vector A is this, and B with position vector B is this. So why not? Let's go for that then. So vector line equation, there seems to be one here, and also in the question there seems to be another one here. So it makes sense that rather than calling it R, I'll just call it R1 for this first line here. Do you see? So it helps if I write A is, well, 3, 8, and careful with that minus, okay? Always look at the signs. If that's a minus, then that's got to be a minus in your column matrix as well. So now we've got 5, 7, and 1. And as you know, again, if you ever feel like you're like, I'm not sure, just draw that quick picture. So to describe any point on that line, you're first going to go A, aren't you? Plus lambda, your direction vector, which is going to be A to B. Do you see? So plus A to B. And A to B is last thing minus first thing. So B minus A. You can clearly see that, can't you? In order to get from A to B, I go minus A plus B. So this is going to be 3a minus 2, that's a, and lambda b minus a, so top minus top, so 2. 7 minus 8 is minus 1. 1 minus minus 2 is 3. And there we go, there's line 1. Second, find the vector line equation between the points C and D, and C has 7, 4, and 3, and D has 9, 5, and 7. So we can go much quicker now, can't we? So R2 is going to be C, 7, 4, 3, plus, not lambda this time, because that proportion and that proportion, you don't know that that's the same. Do you see? You don't know how equally spaced A, B, and CD are relative to their own lines. So 743 plus mu, lots of C to D, which is D minus C. So 9 take 7 is 2, 5 take 4 is 1, 7 take 3 is 4. There you go, you've got your two vector line equations. We can whack this into autograph to see, we're going to use the maths to show me, but the question is, do these two lines intersect? And let's see if they do on autograph. So if we go for clear the ink, if we go for, let's get rid of this stuff, get rid of that, get rid of that, get rid of that. Cool. So our first line was first line 3, 8 minus 2, so 3, 8 minus 2, and the direction vector was 2 minus 1, 3, 2 minus 1, 3, bang. Next one, so 7, 4, 3, 7, oops, 7, 4, 3, and then 2, 1, 4. 2, 1, 4. I know it says lambda there, but it's just for the computer program. It's not actually lambda, it's mu, lots of that. So here we go. You can see from the diagram that, yeah, it looks like the lines intersect. So let's prove that they intersect, and let's see why that is, or how that is. Well, remember what R means. R, in both cases, means point, any point on the line. I'm going to keep reiterating this, because this is where, you know, if you understand this, then you can do most problems. Any point on the line. So if they intersect, then therefore those points on both lines, so if this is line 1, so that's, let's call this R1 here, line 2, yeah, so line 2, line 1, R1 and R2 must be the same point, mustn't they, if they intersect? There's a point on both lines where they both marry up with each other. So if they intersect, R1 must equal R2. Yeah? So therefore, R1, which is 3 plus, and now you can write this as one matrix, right? So as one vector. 3 plus lambda 2, 8 plus lambda times minus 1, so 8 minus lambda. And we've also got minus 2 plus 3 lambda. And this equals, on your right-hand side, so number 2, 7 plus 2 mu. So you see how you can put them all into the same vector, 3 plus 4 mu. And now you've got 3 sets of simultaneous equations. Do you see? Because you've got 3 plus 2 lambda, top must equal top if they intersect, middle must equal middle, bottom must equal bottom. So what we would do is, we would write 1, 2, 3. So, if number 1, 3 plus 2 lambda equals 7 plus 2 mu, and number 2, 8 minus lambda equals 4 plus mu, now we've just got kind of a GCSE elimination problem, don't we? So if we times the second one by 2, that gives me 16, because I'm trying to get rid of a 2 lambda, 8 and 2 mu. Can you see if we add them together, there we get 3 plus 16 is 19. The lambdas cancel out, which is exactly what we wanted. 7 plus that is 15 plus 4 mu. And therefore, bring the 15 over, that's 4, and mu must equal 1. Do you see? Now, if mu equals 1, sub it back into that first equation, let's say. So 3 plus 2 lambda, so 3, box that one off, 3 plus 2 lambda equals 7 plus 2 mu, which is 1, gives me lambda is, well, 7 plus 2 is 9, minus 3 is 6, divided by 2 is 3. So at the moment, we found mu and lambda, but if they intersect, then the third equation must work too. So this is your check, and you must do this check. It's not just me saying it this time, you will lose a mark if you don't do it. Because just because top and bottom are the same, it doesn't mean the z element is the same. They may still meet x and y wise, but not z, so you must check that. So in number 3, this is a simple, does the right hand side equal the right hand side? So lambda was 3, isn't it? So that's that equation. Minus 2 plus 3 lambda. Does that equal 3 plus 4 lots of mu, which is 1? Well, here we get 9 minus 2 is 7, and that does equal 7. Therefore, intersect. Do you see? Done. And that's it for that video. Now we've got the dot product.